So I can start at least introducing today's lecture. So this week is the last week. Today, I think, this is the last time we talk about discrete logarithms, at least. And then Friday we'll see a few more Excel little things study up, and then we can move on. Okay, we can see some information theory and another little amount of stuff. Okay, so but I did want to show you polar draw algorithm, partly because this is like a really cool algorithm, and it's important to understand how this kind of collision algorithms, probabilistic algorithms work. And we also built a decent baggage, although fast, of probability background, which is going to be useful anyway, but it's kind of really useful here. Okay, so the idea of Pollard's method is the following. Basically, we already have a collision algorithm that works, but it takes a lot of space, storage space, and it's not practical. And it can certainly be improved, not even just on the size of space, but in general. Okay, so that's kind of like an intuitive observation, but we can do better. Okay, so let's see first the idea at a higher level. Okay, and so one key component of the raw method is a function f. I should say this is section 4.5, I suppose. And this is lecture 18, 19. Okay, so suppose that we have a function f that takes values in a set S into S itself, right? So S is like a finite set, and it's a function that kind of scrambles up the elements, so has kind of like a random looking output. Okay, so f is kind of like random looking output, and it mixes up the elements of the set nicely. Okay, so this is going to be an important component. Now, let's take the function f, and let's say we have a starting point x, first element. What happens if we apply f repeatedly? Yes, so we can set a chain. For example, x0 is x itself, and then we set x1 to be f of x0, right? And then x2 is going to be f of x1, blah, 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 blah. And in other words, basically what I'm doing is I'm just going to do xi equal to f of xi minus 1, which is f of, or if you want, is f of, well, it's kind of, let's do composition because it's easier to write rather than a lot of brackets. Okay, so it's just f composed with f I times applied to x. Okay, it would be f of f of f of f of x. Okay, so what I'm doing is I'm taking the main ingredient, which is a function that scrambles up the elements of the set nicely, and then I apply it, starting from a starting point. I apply it over and over again, and every time I apply f, I get kind of like a random looking element, right? So I do what is known, in fact, there's two key components. The first one is a walk, because I'm walking on the elements of the set, right? But most importantly is a pseudo-random walk. Okay, so it's pseudo-random because, of course, like everything, is not true randomness, right? But it is kind of walking on the elements of the set in kind of like an erratic, randomly looking way. Okay, so this is a very important concept of pseudo-random walks. And pseudo-random walks are important because, of course, they give really good results in this kind of algorithms. Okay, so a lot of the algorithms that traditionally they are used to like attack things, they do a very good job of doing that. Okay, so this is like a first example, and I haven't even told you. What the function f is. In the book, they also define f as an example of a discrete dynamical system. Okay, so if you know what the dynamical system is, it's kind of the culmination, if you want, of the whole calculus branch. A dynamical system is a system that changes over time, and you traditionally study these using derivatives and differential equations and this kind of stuff. So to study like populations of animals and other things, like these are all examples of dynamical systems. But when we talk about a discrete dynamical system, like everything else, discrete refers to discrete objects like finite sets and things like this. And, and so a function that behaves this way is an example of a discrete dynamical system. And if we start from the element x, then the sequence of elements x0, x1, x2 is what we call the orbit of x, right? By f. Cool. So we keep applying f to x, and this gives me an orbit. And the word orbit is interesting. It's a concept that appears in other areas of mathematics, of course, as well. So it's just basically what's the orbit? It's like when you launch a satellite or a planet or something. The orbit is the path, right, that the thing goes over. So that's kind of the same idea by analogy. Like if I start with an element, what's the orbit of the element? It's the path that the element follows, right, over the elements of the set. Okay, so we can actually like visualize this orbit. And here's what happens. And I'm gonna try to be, I was never exactly an artist, but I'll try to draw these things clearly. So I start from x0, which is x. And then like I take a step and I get into x1. And then I take another step and I get into x2. And I keep doing steps, right? Suppose that at a certain point I arrive at a step x t minus 1, okay? And I keep walking across the set. So we'll see why this is called t. Then I take a next step is going to be xt. And I keep going, xt plus 1, t plus 2, etc. But what happens is that at some point, I'm going to connect back to a point that was already happening. And the reason is, you would tell me, of course, that the set S is finite. So if I keep like doing random walks, at most, I can hit each element of the set once. Of course, that's never going to happen actually with any reasonable probability, right? So at some point, I'm going to have an element x, say m plus t, which is equal to xt. Okay, makes sense? So I keep walking, but you see that it starts looping around. And so I distinctly can talk about a tail, which is of length t, say, and then a loop, which is of length m, if you want. Okay? It's not standard notation, but there's definitely a tail and a loop, and it makes sense to call t for the tail. I don't know why m for the loop, didn't want to use L. Okay? But clearly, that there is going to be a tail of elements that are hit distinctly, and then the first element of the loop, is the first element that is duplicated. After you hit that, then it's just going to keep looping. Right? And if you look at this shape, well, that kind of really looks like the rho. This is the Greek letter rho, which is the letter for the R sound, Greek, and that's why this is called the rho algorithm. Okay? Because it's got the tail and then it loops around. Okay, so here is basically what happened is that we draw out the orbit of the element x, and then we get a tail and then a loop. And the tail basically is of length t, and it's like the largest index, which is an integer, such that x, say t minus 1, appears once, right? And this is the smallest index, such that x t plus m is equal to xt. Okay. So we have to take the largest and the smallest because, of course, like it keeps looping. So you could say like, oh yeah, this is the length, right? So, but hopefully this is clear. Now, okay, let's suppose that the cardinality of S is, let's say, big N. So it's got n elements. Okay. So usually the interesting property, of course, what's the intuition here? You like the loop, right? You like this. Because that is what? A collision. Okay? So you're interested in knowing what is t plus m essentially, and what we can see is that essentially this is more or less say like order square root of n, but in fact it's like usually a small multiple of square root of n. Okay? So you're likely to find this collision quite early. Okay? So basically, at this point, we have this idea of doing a walk, just a random walk, and then at some point you're going to get the loop. And then it looks like you have to write down this list of values to detect the collision. But, so on top of this, and what Pollard's really cool idea is that you actually don't need to explicitly list all the elements in order to find the collision, and we'll see exactly how this is achieved. Okay, so we'll see one method which is easy to understand. It's probably not the optimal one, but it kind of gives a blueprint for how it works. Okay, so we have now a sequence. We have now a sequence of elements xi, which is built starting from a certain element x and applying f repeatedly. Yes. Now let's build another sequence, yi, and we start at the same point, okay? But we create the next element by applying f twice. Okay? So instead of going basically one f step at a time, we jump steps. Okay, so we have x0, and then we have f of x0, and then we have f of x0. That creates the xi's. But the yi's is y0, which is the same starting point, and then f of y0, and then 4 times, and then 6 times, and what. Okay, so we go 2 steps at a time. So basically, in other words, we have that yi is the same as x2i, because we skip all the intermediate steps. Okay, so how long will it take me to actually find an index I, right? I want to find a collision, so I want to find a certain, let's say, xi that is equal to x2i for some value. Okay? So if we consider, say, j greater than I, then the condition, let's look at the condition. We have that xj is equal to xi if and only if, first of all, I has to be greater than the tail. I have to be in the loop, right? And then j has to be congruent to I mod m, because m is the length of the loop, right? So look at this condition. I'm trying to find one value such that one of the elements hits one of the elements in the other sequence. Yes, and if now I think that one is a j and one is an I, of course the smallest of the two needs to be already out of the tail, otherwise this will not happen, and they have to be congruent modulo the length of the loop. Yes, because that is how the two will be equal. You can really just think at the picture, right? You have to be already like in this loop here. Okay, so basically, if we do this for this, if we're looking for a specific index, then we can just think that the j is the 2I, right? And therefore, the condition is that I has to be greater than or equal than t, and then 2I is congruent to I mod m, okay? So if I was just writing out the sequence of the x's, then I'm looking for this condition here. But if I'm writing out two sequences, and one has the xi's and one has the x2i's, then I'm really looking for this condition here. What's a 2I that is congruent to I modulo m, right? And you know, the 2I would be element of the y sequence and the I would be element of the x sequence. But this is easy because this is the same as saying that I is congruent to 0 mod m. If you just subtract I from both sides. And so that really is the same as saying that m divides I. I is a multiple of m. Okay? So basically, we get this correlation that we're interested in between the two lists exactly when I is the first multiple of m that is larger than t. Okay? So we do our tail, we keep going, and then at some point in our loop there will be a multiple of m that is larger than t, and that's going to be exactly my collision there. Okay, between the two lists, they kind of overlap, and at some point they'll match. So now, what we can consider is that basically what we're taking is we take t plus 1, t plus 2, all the way down to t plus m minus 1, which is the last one. That's the elements in the loop. So basically, one of these numbers here, it has to be divisible by m, right? Right, because there's m elements, so one of them needs to be a multiple of m. Is m distinct elements. So clearly, there exists one index I among these ones that is the one we're looking for. Okay? This is the idea. Already we kind of gave a hint. We basically, instead of writing out the one list and looking for collision, we write two using the same functions, and so they kind of like overlap, and then at some point you find one that collide for an index that is among these ones. And we will show that on average, it takes something like 1.25 times square root of n, so that's not very much at all, right? But what is the advantage of this is that now I'm calculating x and y lists, but I don't really need to store these lists, right? I compute the x value, and I compute the y value, and then I check if they match. And then I move on to the next. So I store one index at a time, or the value, I check one index of the value at a time. So I only really need to store two numbers at a time. Okay? So that's very cool. And so let's see this second part. The first part, we've kind of already proved that we are going to find a collision. Let's look at the expected. So the expected value for t plus m is in fact about 1.25 times square root of n. Okay, so of course this is not going to be an extremely rigorous proof, but just again the intuition. So suppose that we take the first k values, x0, x1, xk minus 1. Okay, what is the probability that we get no matches? Yes, as usual, we're going to do calculation in this way, computing the probability that we don't get a match. Okay. Well, we have to assume that my function f does a good job at scrambling, and so all these x0, x1, x2, they're kind of like picked at random, right? This is why I want my function to behave randomly, so I can make considerations of probabilistic nature, and I can just assume that they're randomly drawn. If they're randomly drawn, then the probability of x0, x1, xk minus 1 being all different is the same as the product from I going to 1 to k minus 1 of the probability that xi is different from xj for j less than I greater than 0, right? So one I at a time, I fix the first one. Then the second one has to be different from the first one. Then the third one has to be different from the previous two. And the fourth is it, right? Given, so it's condition probability, then the x0, xi minus 1 are all different. Right? So this is not tremendously formal, but the idea is the following. I compute this as a product of probabilities, given that the previous ones are all different. What's the probability that the next one is different from all the previous ones? And then I take the product, but this is easy to compute. This is the product of exactly n minus I divided by n. Okay. The first one, of course, is going to be n minus 1 over n, because you have just one element, and then you just keep going in this way. Okay. Then you get n minus 2 over n, because you fix two elements and whatnot. Actually, this is the same as 1 minus I over n. That's a 1. Okay. Actually, so this product is kind of in a recognizable shape, and we can approximate it if we use this estimate that 1 minus t is approximately e to the minus t for large enough for small enough values of t. And therefore what we get is that this product is equal to the product of e to the minus I over n. And this is a more useful estimate because this is essentially approximately e to the minus k squared over 2n. Right? This is e to the minus 1 over n times e to the minus 2 over n. So it's minus 1, minus 2, minus 3 is minus 1 plus, all the way it's a summation of the top. And the summation is approximately k squared over 2. Okay. So there you go. So basically, yes, so we use the fact that the sum of I is equal to k squared over 2. Yeah. It's a well-known summation thing. So now, assuming that they're all distinct, we have selected x0 up to xk minus 1. We don't have a match. What's the probability that the next one is a match? Given, so the probability that xk is my match, given that the x0, xk minus 1 are all different, is actually k over n. Because we have exactly k elements to match, right? And so if we put the two things together, here we assume that the probability is all different, is this one, is this one. And here we say, okay, what's the probability that xk is a match, given that they are all different, is this one. So all we need to do is the product, right? And really, the probability that k is the first match is the same as the probability that xk is a match, right? Given that these are all distinct, times the probability that these are all distinct. We've learned the conditional probability, right? This is like probability of E given F times probability of F, right? Because that is the same as the probability of E and F, okay? Or intersection, if you want. That's what we learned last time. So this is a simple calculation. It's going to be this one times this one is approximately k over n times e to the minus k squared over 2n. Okay? So then, the expected number of steps, and I'm going to switch, is piece of paper, the expected number of steps is definitely the sum of k times the probability that xk is the first match. Remember the definition of expected value, right? Is the value of the random variable times the probability that the random variable takes that value. So if I take my random variable to be the first match is k, then I got k times probability of x equal k essentially, and I sum over k, k greater or equal than 1. So it's k times the thing that I had before. Is the sum k times it was k over n times e to the minus k squared over 2n. And now we get to a point, look, I'm summing over k. So this is really not a finite sum, right? It's an infinite sum, because I don't have an upper bound. And so actually if I look this as a series, and see what this looks like, what I'm interested in, of course, I'm looking for this is the expected number of steps, right? And so I'm looking at this as a function of n, because I want to know if my set has got n elements, that's where I started from, right? As a function of n, how many steps do I have to take? Remember that I'm trying to get to that 1.25 times square root of n. So here's what I can do, and that's why I think that this is kind of cool, because it mixes a lot of things. We already saw some algebra and some probability, and now we're going to throw in some calculus. And the result that we are interested in, if you want, this is just a little lemma, but if I have a nicely behaved function, f of t, and you all know what it means to be nicely behaved. In calculus, for example, there is like continued, with continuous derivative and like not anything crazy going on. And we want the property, so it's like nice, okay? And then the property that I want is that the integral of f of t from 0 to infinity, let's say t is convergent. So remember, this is an improper integral, and by convergent it means that when you take the limit to infinity and blah blah blah. Then what we can do is that for large n, so then for large n, we actually have the sum from 1 to infinity of f k over n is approximately n times this integral. Okay? So if I sum the function in k over n, then it's exactly n times my improper integral. And basically, I mean, I don't want to go too deep in the proof, but you can see that by definition, my integral here, my integral from 0 to infinity of f of t dt, it's basically the limit so basically we take this up until a certain number a, and this is going to be the limit for n going to infinity of the Riemann sum. Sorry, that's k an f of k over n times 1 over n. When n goes to infinity, I get this limit, and we've basically broken up the interval from 0 to a into n pieces. Then we do the usual thing that we do with Riemann sums, that we send n to infinity, and the pieces get smaller and smaller and smaller, and I get exactly the integral, right? And then we kind of, we can kind of approximate, because we have a 1 over n. I'm going to multiply by n on both sides, so I get an n in front here, right? And then basically I just send a to infinity here, because that's a finite integral. I don't want the improper one, so then I just send a to infinity, and that gets me my result. Okay, because here on the left I get this, so it's n times this, and then I replace a to infinity, because I send that a to infinity. And on the right I have exactly f k over n. Obviously here a and n both go to infinity, so I get this sum to infinity here. So it's very hand-wavy idea. It can be formulated more precisely, but what you care about is this result. When n is large enough, then you can approximate this sum with this integral. Now you have kind of a sum that reminds you of that. Okay? So basically, we have that the expected value of the first match is that sum up there, right? And I can actually write this as a sum k greater or equal 1 as the same as writing from 1 to infinity, right? Of f of k over square root of n, sorry, that's the bracket. If I call my f of t the function, check that I'm not making mistakes, t squared e to the minus t squared over n, over 2. I already told you, check that I'm not making mistakes, okay? Now if you replace t with square root of n, you get exactly n, sorry, it's with k, k squared over n, right? So that's k squared over n, so it's that part, and that's k squared over 2n, this part here. Okay. So this is exactly a function. Now I can use my estimate from that. So this is going to be approximately, remember my estimate tells me this is n, in this case n is my square root of big N, so it's like approximately the square root of n, okay, times the integral from 0 to infinity of my function, which is t squared e to the minus t squared over 2 dt. And this is why do I care? So it looks counterintuitive because I have a sum and approximate it with an integral. How is that getting me anywhere? And the answer is that there is an entire part of mathematics that is numerical analysis that is devoted to evaluating things exactly like this integral with numerical methods. And you usually get a glimpse of this in your calculus courses when you start doing those numerical simple methods to evaluate, to approximate the integrals, right, with the intervals and the midpoint rule and whatnot, and then you can kind of like take this to the extreme. But basically, if you insist in that direction and you like that, that's numerical analysis there. So you can actually calculate the value of this integral approximately, right? And that is exactly that 1.2533, with whatever precision you want to get, times the square root of n. Yes, so you can actually estimate pretty accurately the value of the integral with numerical methods. Okay. Actually, the value in this case can even be computed exactly. It's not easy, but it can be, and it's, I think, square root of pi over 2. Okay. But again, there's always the difference because we already saw in calculus that there's ways to compute the integral exactly, but at a certain point you don't care if your approximation is good enough, because maybe the difference is in the like 20,000th digit, right? So it's basically the same value. So you don't care that the mathematical nicety of having square root of pi over 2, you just say it's 1.25 and that's good enough, because you're estimating things already anyway. Okay, so you can actually check basically how accurate these three values are. The first value is the actual value, which is essentially, look, the sum for k greater or equal 1 of k squared over n times the product of I equal 1 to k minus 1, 1 minus I over n. That is the raw formula. Okay. The second value is, we approximate already the second part if you want. So we're just left with the sum, k squared over n. We approximate this product with the e. Okay. And the third value is the last approximation, which is the square root of n integral 0 to infinity of t squared e to the minus t squared over 2. Okay, so that's what we're trying to calculate. This is the first approximation. This is a further approximation. And if you look at this, I'm going to zoom in. maybe a little bit too much. You can see, look, for n equal 100, the values are like, the actual value is 12, 210, and this is 12,533, and this is 12,533. So already, the difference between the second and third estimate is not noticeable up until these first few decimal digits, right? Even for n equal 100, it's still a little bit different from the first, from the actual number. But as n grows, you see that the numbers get like really closer and closer. And in fact, if you do the ratio, right, between the actual number and the, say, third approximation with the most extreme, here is like 0.97, but it keeps growing closer. This is 0.99881. So it's really, really, really close to 1. Yes, so the approximation is actually really good. And when n grows, this is only n equal 50,000, of course. That's not an n of cryptographic interest. So you understand, the approximation is actually pretty accurate. Okay, so I thought it was interesting to see some numerical examples to see like, oh, look, actually this, this is why we feel confident doing all these estimates.
Do we actually have a bound on the error?
A bound, that's the bounds that we use, like the one with like the approximation with the integral, that's
No, I mean, what's the error bound?
No, I'm not aware of that. But clearly when you,
Clearly numerically it looks close, but...
Yeah. But of course, the way that they derived, there's a proof for this. And I suppose that in part of the proof there's, which is not this one. This is kind of like M wavy, right? But you can kind of see why at every step it's supposed to be close. I don't think that there is I don't know about the error bound. So it suffices to know that essentially when n is very large, remember that the n that we're interested in is kind of like at least like say 2 to the 80 for what is considered nowadays like a not so strong level of security, maybe like 2 to the 160 at the very most, unless you want to be crazy, okay? So it's definitely reasonable to estimate the actual number with say this number here. Okay. What is good for us now at this point, all of this was to show you that we can get collision with 1.25 times square root of n steps. Okay? So, what do we do with this now? Because now we have just introduced the generic idea of the polar method, which is two things. We start with a pseudo-random function that does this walk. We'll get a tail and then we start looping. And then we know that at some point we're going to get a collision. And the point is pretty soon, so that's good. And the second trick is that we want to do it in a smart way by using the sequence x and the sequence y, which is basically like double the steps, or half the steps if you want, anyway, like apply function twice. So this way we don't have to store the list. And okay, so let's see how we use this in practice for solving discrete logarithm. Because obviously that's always where we're going to end up. The notation here is a little bit different. I don't know why they changed it, but basically the discrete logarithm here is set up as g to the t equal a. And we're doing this for fp star, just to keep it simple, okay? And to keep it even more simple, suppose that g is a primitive root, okay? And, okay, so the idea is that we want to find a collision. And again, I really like this algorithm, it's quite clever. So the collision is going to be a g to the I, a to the j type of element with a, say, g to the k, a to the l type of element. Okay, so that's how we build our lists. And the idea is that we know these four exponents. Once we know these four exponents, we can just rearrange things, right? Then if these two things are equal, then obviously g to the I minus j is going to be equal to a to the, I lost, this is k. And then this is L minus j, I think. Yes? Okay, well, I'm just dividing. Right, so if we know these four exponents, then I know that g to this is equal to a to that. And then I take, basically I can take roots and I can kind of solve the problem that way. Okay? So what's the hard part? It's actually finding a function that does the job. Because it all started at the very beginning. Suppose that we have a function f that does this. What's the function f? A simple one that Pollard suggested in the original work was this one. And again, I think this is very beautiful because it brings a lot of parts of mathematics together, but also it brings a very nice example, because you always see, like, at least with my calculus students, for example, and algebra students, like these piecewise functions. It's like, oh, why do I have to bother like studying these piecewise functions, right? But they're actually, piecewise functions are like super helpful in a lot of situations, whether you actually do calculus and they model some sort of physical phenomena. They do like this and then that and split and things. But in this case, we actually also use a piecewise function, right? So piecewise functions are like a really, really important part of mathematics. They're not just like an odd artificial object that people build. So the piecewise function, in fact, has three pieces. The first piece is gx. So my function starts from an element x, multiplies by g. And then the second piece is it actually squares it, or it multiplies by a. And I want this to be done at random, essentially. Yeah? So I either say multiply by g, multiply by a, or square the element. And I do this at random. So at random, what I mean? I have like basically three options. I divide the interval in three, right? So let's say that I do this if x is like less than p over 3. So in the first third of the interval. And I do this if this is less than 2p over 3. So in the middle part of the interval. And then I do this if this is in the third part of the interval. Okay? So I start from a random number x. If my x is in the first third of the interval, I multiply by g. If the x is in the middle part of the interval, I square it. And if the x is in the last part of the interval, I multiply by a instead. Remember, g and a are these elements here. Okay? So this looks like pretty random to me, right? And why is it random, of course? Because I'm working in fp star. So you see that there will be a tail. For example, if I start from a really small x, right? X is very small. Obviously, it's going to be in the first third, right? I multiply by g, multiply by g, multiply by g. Eventually, I'm going to go over p, and then I reduce modulo p, and at that point, I go into like one part of the interval that I don't really know if it's the first, second, or third of the interval, right? And then what happens is, oh, maybe I square it, and then I end up in another part of the interval, or multiply by a. Depends on how big g and a are, right? So the whole thing is like quite confused, which is good. Basically, it makes sense that if I do this kind of operation, every time I end up in like a different third of the interval, and then I do a different thing to it, then it like behaves really randomly. Okay. So the secret is that this works because I reduce modulo p, and every time like that would throw me into like one random part of the interval. Okay. So this is no one actually proved that this function is sufficiently random. But experimental evidence shows that this works. Okay? It's hard to prove. The functions actually have random behavior. Okay. Now it's a different matter to say that is this the optimal function. In fact, it was proved that this is not the optimal function. That there are better functions to do the job. But of course, it will be more complicated than this, right? So this is good for the purpose of explaining how the process works, and it can be improved, of course, in practice. Okay. So, in fact, here is the fascinating part. Suppose that we start. The simplest point I can start is x0 equal 1. Okay. This is an important step. Okay. So let's be on the piece. So at each step, we basically either multiply by g, or multiply by a, or we square the element. Okay. So in the end, after I do a bunch of steps, xi, I'm going to have, this is like f composed with f a bunch of times of 1. So I'm doing this for 1 so I don't corrupt the element with the original stuff. Basically, what this is going to be g to a certain power times a to another certain power, right? And this is alpha I, say, and beta I. Okay? Makes sense? Because I only ever either multiply by g or multiply by a. There was nothing in it to begin with, it was just 1. That's why I said there's no other factors in that. So it's going to be a certain power of g times a certain power of a. And what happens if I square? I double these, right? So there's no other components there. It's just a bunch of g's and a bunch of a's. Okay. So really, rather than looking at the actual number, what I can do is look at just the exponents. Right? And in fact, when you think about it, the first exponents are obviously 0, because I have 1, so it's g to the 0 times a to the 0. And then at every step, I can model the behavior rather than the function itself of the exponents. Right? I have that a alpha I behaves in the following way. The next alpha is going to be what? The previous alpha plus 1, because I multiply by g, right? So I get 1 more g. If x is between p over 3 and 0 in the first interval. Right? So yeah, I start from a certain point. What's the next alpha I going to be? If I multiply by g, this increases by 1. This happens when x is in here. Or, if I square it, I double it. Right? Because I take the square, so obviously the exponent is double. Or, it's going to stay the same if I multiply by a. Okay? These are the same cases that I had here, so I'm not going to write it again. Okay, so that's the behavior of the alpha I. At each step, alpha I either increases by 1, doubles, or remains the same depending on where my x was. Obviously, you can do the same thing for the beta, which either stays the same, doubles, or increases by 1 in the opposite sequence of events. Right? So you can see, you can model the behavior of the alpha and the beta exponents. You can just look at how many times G appears and how many times B appears. How many times G appears and how many times A appears. Okay? So basically, we can just look, rather than the G and the A, at the exponents. And in fact, what we're going to look at it is modulo p minus 1, of course. Because you remember that obviously we're working modulo p, we have Fermat's little theorem, and blah, 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 blah. So we're actually looking at these exponents modulo p minus 1 as well. So that keeps them very small. Because after a while, otherwise these exponents, of course, will become huge. Right? But we want to do several iterations and keep track of the values of the alpha I and the beta I. Okay? So this makes sense. We start from x is equal 1, we apply f a bunch of times, and basically the only thing that happens is either I multiply by g, or I multiply by a, or I square. And if I square, actually, I'm touching both exponents, right? In the other two cases, I'm actually increasing one or increasing the other. Okay, so now, so this is how I deal with the x. But with the y, I can do the very same thing, because remember, I can also start from y0, which is equal to 0, so 1, and then compute yi plus 1 as f of yi. And therefore, what I'm going to get is that yi is x to I, which we knew already, and this is going to be a certain, say, g to the gamma I, a to the delta I, okay, for the same principle. I've just multiplied by g and multiplied by a bunch of times. And actually, these exponents gamma I and delta I can be computed from the previous one, because I just do 2 repetitions of the process that I did for the alpha I and the beta I. I just do it twice. So, so basically, the first time we use yi, and we determine what happens to the exponent, and the second time we use f of yi, and determine what happens to the exponents. And that's how I can keep track of my gamma I and delta I. And you see where we're going. Now we're getting a g to the alpha I, a to the beta I in one sequence, and a g to the gamma I, a to the delta I in the other sequence. At some point, I'm expecting these to be equal, right? So when I do find the collision, what I'm going to find is that g to the alpha I, a to the beta I, is going to be equal to the g, gamma I, a, delta I for a certain I. That comes from the first list, that comes from the second list. And so now, of course, we already anticipated this. What we can do is call things differently. Let's say that I take alpha I minus gamma I and I call it u. This happens mod p minus 1. And similarly, I equal v, the delta I minus beta I, again, modulo p minus 1. Remember that all exponents live modulo p minus 1. So I take u and I take v, then this means that g to the u is equal to a to the v in Fp. Star. Okay. And this basically solves my problem, because I can also write this actually as v times the discrete logarithm of u is equal to, this log g of a equal to u. Okay. Yes. So that's the discrete logarithm I was interested in finding in the first place. And if I know u and v, then this obviously that's like u over v. So I'm done. In fact, I have to be a little bit more precise. I have to assume that v and p minus 1 are coprime. Otherwise, I cannot divide by v. If I do, if this is true, then there exists an inverse of v, which means I can divide by v, and I get u over v, or u times the inverse of v, and I solve the discrete logarithm. So in general, if this is not the case, remember that what I can do, if this is a d and is greater than 2, then I can actually use extended Euclidean algorithm and find one relation that gives me the coprime one in which the coefficients are the same. Right? I'm just dividing the entire relation by d, so then that still works, and I get something like this. I get the s times v is congruent to d mod p minus 1, right? Because that's the GCD, and then therefore I get the d times log a, log g of a is equal to a certain, say, w, yes, and then therefore w equal w, the quantity s by u. So I'm just multiplying by s both sides, and again, the only quantity that I do not know is the logarithm here. And therefore, because d divides p minus 1 at this point, we have that d has also to divide w, and so we get w over d to be one solution to my discrete logarithm problem. Now, of course, because this is not one, I could have more than one solution, right? I could have the solutions are of the form w over d plus multiples. Remember, I'm working modulo p minus 1, so it could be something like k times p minus 1 over d for a bunch of k's. And one of those is going to be the solution that I'm looking for. Okay, but this set is not too big. This set is not too big. It's up until d minus 1. And in fact, remember that the trick is that the p is usually chosen so that I only have like one large prime factor, because otherwise Pauli-Gellman. And therefore, because I only have one large prime factor, it's very unlikely that d is divisible by that large prime factor. So I don't expect this to be very big. Okay. So I can just check these values, and I'll find the one I'm interested in. Okay, so this is kind of like the idea. I mean, if you look at this, this is what we're looking for, and that's what we kind of already anticipated. Right? We just have the two lists, we're looking for a match, and at the point we just kind of like rearrange our exponents, and basically we're done. We've kind of solved by taking roots, essentially. Okay. So here is a numerical example, which is not just fancy, but I think is also interesting. Suppose that I'm trying to solve 19t equal to 4717 in F 48611. Start, because that's my G, that's my A, and that's my P. Okay? So we start to compute the X and Y sequences, and we start from 1 until we find a match. Okay? And this is what happens. So I'm going to zoom a little bit in. So we start from 1, and y1 is also 1, so this is the first element, all the exponents are 0, right? Then I go, okay, that's 19, I apply f twice, so the first element of the second list is 19 times 19. And so you see that the first exponent here is 1, because I have 1g exactly, and here I have 2 g's already, g times g, okay? I multiply by g because obviously 1 is in the first third of the interval. Yes? Okay, so now in the first list I get 19. 19 is again in the first third of the interval. The interval is 48611. So it's say, I don't know, 13,000? No, maybe like 17,000 or something. 17 times 3 is 51, whatever, 16,000, something like that. Okay, so if x is less than that, I'm in the first third. If x is in between, I'm in the middle. If x is big, I'm in the last third. Make sense? So now you see there is this initial tail. So here, what do? I'm going to multiply by g again. Yeah, multiply by g again. Boom, I get 361. Here already, I do it twice. In the second list, I'm already over. But at this point, I've got 2 g's here and 4 g's here. So the second list is basically the first one that goes a lot faster. So that's already kind of going to show me that my first list, I'm going to have to multiply by g 4 times. Right? So here we go, boom and boom. So I'm actually, let's just look at the first list, right? I multiply by g and I multiply by g again. Finally, so at this point, it's just my alpha I that is growing. Finally, I get in this part, now my x is big. So in this case, it's big. So I'm going to multiply by a instead. You see, haha, that's the first beta that appears. Okay? Okay, then I reduce modulo p, and I get here. Oh, this is still big. You see, now it starts being random. Because I multiply by a, I had a big element. When I reduce mod p, I have another big element. So it's going to be another beta there. Okay? And then I keep going. Oh, now this is small again. It's in the first third. So I'm going to multiply by g again. You see that my alpha is growing. And then I keep going. This is still small, so multiply by g again. This is in the middle, and I square. And see what happens when I square? First exponent is doubled, and the second exponent is doubled. Okay? And that's kind of where the experiment stops, because of course you understand the pattern now. And if you look at the second column, it's got the same numbers, except it skips one step every time. Right? So it goes 2, 4, 4, 2, 6, 2, which are exactly this one, 4, 2, and the 6, 2, right? And so it just goes at twice the speed. Yeah. So it grows quite fast. And then you'll see that the gamma is 228, the delta I is 80. This is very convincing, the fact that this is random, okay? Okay. So I'm going to zoom out again, and we can just finish. At some point, I will find a collision. Actually, okay, maybe before I do that, I will show you that we do get the collision. It's here. Here. You get 33252 in both lists, finally. Remember that, my exponents obviously here are small, right? I keep doing this. This is step number 548. Of course, if I keep multiplying a with itself, increasing a, it gets really big, right? So look at the alpha I. It's huge. And here, so obviously I have reduced modulo p already up here. See, I have reduced modulo p minus 1. So my exponent at these points behave also like random numbers, essentially modulo p minus 1. And so these are the 4 exponents I'm looking at. 1, 2, 1, 3, 3, 21, 5, 5. And this is my exponents. For this magical combination of exponents, I get the match that I was looking for. Okay, now I can take this off. And okay, so now what I found is that x 1096 is equal to x 548. Okay, because that's y, this is y 548. So it's x double that. So that's my I. And that's x2i, which is yi. Okay? And now, yes, they are both equal to 33252. Bang, I found my collision. I take my exponents. Alpha 548 is 1, 2, 1, 3, 3. Beta, I'm just gonna write I 2155. Gamma I was 47273, and delta I is 4,665. Okay, these are my 4 exponents. I just have to finish. So I know that 19 to the power of this times 24717 to the power of this is going to be equal to 19 to the power of this times 24717 to the power of this. Right? And of course, we check the equality that it makes sense, it is correct. Now I move the powers of 19 to the one side, move the powers of the 24717 of A to the other side. I get that 19 to the negative 3514. Of course, I'm going to take this modulo, right? P minus 1 eventually is equal to 2477. This is just the raw calculation, 26510. Of course, I get a negative because this is much bigger than that. It doesn't matter. In the end, I'll take the modulo P minus 1. So I get 19 to the 13470 equal to 24717. That stays the same. Okay, I got my candidates here, my U and V, how we call them up there. And okay, then it's basically just a check on the GCD now to see what the next step is. 26510, let's check it with P minus 1, which is 48610, right? Because if this is 1, we're good. If this is not 1, of course, in this case, it's not going to be, it's D. Then I have a little bit more work to do. In fact, I can write that 970 times 26510 gives me 10. Yes? That's the relation I was looking for, that's my S. So I don't use the original relation, I have to use this modified one. And I multiply by S both sides, which means I take this to the power of S on both sides. So I take the power of 970 of both these, so the exponent becomes this times 970 and this times 970. And I get the 19 to the power of 38420. Of course, this times 970 modulo P minus 1 is going to be equal to 24717 to the power of 10. This we know because we have this. Now I can proceed. 10 times the log that I'm looking for is 38420. Yes? And the log that I'm looking for is going to be 38420 divided by 10. In this case, it's even a simple calculation. I just get the log G of A is 3842. Okay? And this is a starting point. Remember, this is not necessarily the finish because I have a bunch of values to check. Namely, I have this. And then I have to add multiples of a 4861. So I have to add multiples of 4861, which is this divided by D, right? It's P minus 1 over D. Yes, remember it's a clear thing. Because that's kind of like the models that I can get. So I have this, and then I have 8703, and then I have 13564, and blah, 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 blah. The last one is, okay, all the way up to is modulo P minus 1. Okay. So I have a bunch of solutions, there's like a dozen of them, and we just check. We can really just take like 19 to the power of whatever, B, where B is like one of these, okay? And check that that's the actual number that we're looking for. We do this for the first few, it doesn't work, it gives me other numbers. When I do this for B equal 0.37869, I get the correct answer. I get that this is actually 24017. Okay, so if you check 19 to the power of this, and this, and this, and this, and this, modulo p, of course, you get different numbers. So those were just attempts, but not the correct ones. The correct one is this one. This is one of the last ones in the list, and that's a discrete logarithm. That's it. Okay. So of course, now this last part of computation is not the dominating part, right? You just have to go to GCD, do a bunch of multiplications and stuff. It's not, this list is kind of small anyway. So it's an overhead, but not the dominating part of the algorithm. Right, clearly the dominating part of the algorithm is finding the collision. And we already saw that, look, when I have my p, the exponent is only 548. So it's quite small. In fact, it's, I suppose, less than the square root of n, or what's the square root of that number? If I take the square root of 48611, it's about 220. So it's roughly twice the square root of n, which is okay. It's kind of what we were expecting. Yeah, and so with that number of steps, we find the collision, and the rest is just doing some algebra, essentially, some small overhead.
That's a lot more than the number of steps we were expecting.
Well, the number of steps is like 1.25. That is 2. No, maybe like between 2 and 3. It's 2 point something. You can calculate. So it's a little bit more than the number of steps. But of course, it's just like a random example. Yes. On average, you expected the calculations that you had before to estimate that 1.25. I mean, that's not the law, right? Of course, there is like a probabilistic approximation with like 2 different estimates in there. So sometimes you'll get more, sometimes you get less than that. It's not like, it's not exactly like, but it doesn't matter if it's 1.25, 2.25, 3.25, as long as you know that it's going to be a small multiple of square root of n steps. Because that counts as O square root of n. That's what we care for. And of course, the idea is that we only ever store the previous line of the table, and then we move to the next line of the table, right? So we really only ever storing like what, 2 or 4 integers anyway. Okay. And then once we find a match, we're done. We just read the exponents, and we just do a little bit of computation. Okay. So there's that. And this is all that I had to say for the larger algorithm. So of course, this still falls under the umbrella of collision algorithms, and we've seen that the index calculus, for example, is more efficient when I'm working over FP. But collision algorithms provide a very high standard for all the cases where I cannot use index calculus, like for example for ECDLP, right, over elliptic curves. And for larger algorithms, besides being like a brilliant idea, which I think is very brilliant, the idea of using the tail and the loop and then finding the collision, and there's a lot of ingredients in there. It's quite sophisticated in terms of it shows that like these collision algorithms actually have like a very deep probabilistic component. And in general, when you start doing things for serious in cryptography, like in any other things, then you're really raising the bar, right? Because the baby step, giant step was really a simple observation, like, oh, we actually find a match in it. But this has like a much stronger component in it. And there's stuff that comes from all other areas. And of course, you can imagine, like, now what people would do in research is take this and like, oh, do I have an optimal choice for my functions? Can I manage to like cut off some steps, accelerate this step, right? After a while, the curve, of course, flattens, like from the first idea of the algorithm, similar to what happened, say, for factoring with the sieving. Of course, the sieve of Eratosthenes is back to the Greeks. That was like 3,000 years ago. So after that, people like improve it, and they have like the number field sieve, and then every time you just kind of like try to file away the little chipping things, right? And then strongly optimize your algorithm. So maybe you get a better choice for the function. Then you have like little tricks you can improve, like the storage thing, and okay, and again, we've seen this with RSA, like, oh, maybe instead of using 2 primes, I use 3 primes, and I do like little optimization. So after is like fine tuning a car, and then the gains are little, and I mean, I've seen research papers that say like, oh, I managed this new method, and I reduced the exponent in the complexity by like 0.6. Okay, so instead of being like n to the 2.4 is like n to the 1.8 or something like that, and that's a research paper, right? So it's like it's a significant contribution, and you do this with, of course, you put even more complex stuff behind, and you look at, in this case, the main ingredient, of course, is it's entirely on the pseudorandom function, right? But when you look at this, and you're like, okay, what can I optimize? Do I start with one? Maybe there's like an ideal value that I start from. Maybe there's like the function that I can do better. Okay. So it's a good blueprint. I think it's like very important. So besides the importance of this as an algorithm to attack DLP, I think it's also a really good blueprint of what like these cryptographic algorithms look like and what is their kind of like lifespan and how they get improved, and okay. So as I was saying at the beginning of the class, this is kind of like the last thing that we'll see on DLP and the traditional stuff. Friday we'll see a little bit of like information theory and complexity notions just to top it off. And then next week we start with some more modern, not that this is not modern, but like different types of primitives, yeah, different kind of idea. Cool.